Hi, myself Dr. S.K. Bushra, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students. Lesson 3 of the chapter 3. Electrical cells, combination of resistors and electrical energy and power. In this lesson, we will discuss electrical cells, EMF and internal resistance, and then combination of resistors, and finally, electrical energy and power. Let's begin. The first topic, electrical cells, EMF, and internal resistance. In this lecture, the chemical processes taking place inside an electrical cell have been highlighted, although they are not included in the NCERT physics textbook for class 12. Please keep it in mind while going through this part of the lecture. Electrical cells. The earliest method for generating electricity is the electrical or the electrochemical cell. A battery is one or more such cells with external connections. Alessandro Volta, the Italian physicist and chemist, is credited with the invention of the electrical cell. Here is a portrait of Alessandro Volta, 1745 to 1827. An electrical cell converts chemical energy to electrical energy. An electrical cell consists of two dissimilar metal rods or plates dipped in an electrolyte solution kept in a container. The metal rods are called the electrodes. For the purpose of illustration, let us consider a simple voltaic cell. In a simple voltaic cell, the electrolyte is sulfuric acid, that is H2SO4, in dilute aqueous solution, in which H2SO4 molecules undergo dissociations into positive hydrogen ions and negative sulfate ions as per the following ionic equation. The electrodes are made of copper and zinc respectively. In the diagram, the left one is the copper electrode and the right one is the zinc electrode. Zinc, being very reactive, dissolves in a solution in the form of positive zinc ions. As a result, the zinc electrode becomes negative while the solution becomes positive, forming what is known as an electrical double layer. The dissolution of zinc continues until an equilibrium potential difference of 0.62 volts is attained between the zinc electrode and the solution. On the other hand, copper, being less reactive, receives positive charges from the positive hydrogen ions. Incidentally, the positive hydrogen ions bubble out as H2, that is hydrogen gas, after depositing their charges. Here also, an electrical double layer is formed, but with opposite polarity as compared to the other electrode. The deposition of positive charges on the copper electrode continues until the potential difference across the electrical double layer attains the equilibrium value of 0.46 volts. In the adjoining figure, the potentials of the electrodes with respect to the electrolytic solution have been illustrated. The zinc electrode goes down to a potential of 0.62 volt below the sulfuric acid solution, while the copper electrode attains a potential of 0.46 volt above the same solution. Thus, a chemical process in the cell has created a potential difference of 0.46 minus bracket starts minus 0.62 bracket closes equal to 1.08 volt between the electrodes, with copper being at the higher potential. The potential energy of the excess electrons is higher in zinc, which is at low potential, than in the copper, which is at high potential. So, they wish to move to copper, but are incapable of navigating through the electrolyte. Now, if the electrodes are connected externally with a conducting wire, the excess electrons in zinc will readily move to copper through the external circuit. Electrons leaving the zinc electrode upset the zinc sulfuric acid equilibrium. The same bunch of electrons neutralize the positive charges in the copper electrode upon arrival, and thus the copper sulfuric acid equilibrium is also disrupted. In order to restore the equilibrium at both the electrodes, positive zinc ions resume dissolving and positive hydrogen ions resume depositing positive charges in the copper electrode. Thus, ions too resume flowing from zinc to copper inside the cell. The flow of electrons in the external circuit and that of ions inside the cell sustain each other, giving rise to a viable current. The direction of the conventional current is from the copper to zinc in the external circuit and zinc to copper inside the cell. The flow of positive ions from zinc, which is at low potential, to copper, which is at high potential, inside the cell is maintained at the expense of the chemical energy of the cell and is often compared with a mechanical pumping process. Remarks on electrical cells. The simple voltaic cell suffers from two defects, namely polarization and local action. Please refer to some other sources for more information. Of course, methods are available for the removal of the defects. When a current is drawn from an electrolytic cell, its materials get consumed. Such cells, therefore, require periodic replenishments. For example, in a simple voltaic cell, zinc ion reacts with sulfate ion to give zinc sulfate as per the following ionic reaction. Thus, zinc and sulfuric acid are consumed during the process. Examples of other electrolytic cells are Leclanche and Daniell cell. The familiar dry cell, which we use in everyday life, is a modified Leclanche cell. Electromotive force, in short, EMF. The potential difference between the two electrodes of an electrical cell under open circuit condition, that is, when the electrodes are not connected externally, is called the electromotive force, or in short, EMF of the cell. The EMF of a cell depends on the material of the electrodes as well as of the electrolytic solution and is independent of the size of the cell. The EMF of a simple voltaic cell is 1.08 volt, while that of a dry cell is 1.5 volt. The potential difference is defined in terms of energy. The name electromotive force, that is EMF, is therefore a misnomer. It signifies energy and not a force, but the name has been retained for historical reasons. Now, internal resistance. Let us connect a resistor with the electrodes of a cell externally with the help of connecting wires. The current flows in the circuit. The circuit may be equivalently drawn as shown, in which we have replaced a cell with its symbol. Let E be the EMF of the cell, R be the resistance of the external resistor, and I be the current in the circuit. The current in the circuit encounters opposition not only from the external resistor, but also from the elements of the cell. The resistance of the elements of the cell is called its internal resistance and is an immovable attribute of the cell. The internal resistance of a cell is determined by the surface area A of the electrodes. Internal resistance R inversely proportional to A. Distance D between the electrodes. Internal resistance R proportional to D. Nature and concentration C of the electrolyte. Internal resistance R proportional to C. And the temperature T of the electrolyte. Internal resistance inversely proportional to T. In the figure, the internal resistance R of the cell has been shown as a separate entity for the sake of visualization. Current in the circuit. From Ohm's law, the potential drop across the external resistance is I into capital R, and that in the internal resistance is I into small r. Conservation of energy gives us. This can also be established by Kirchhoff's voltage rule, as we will see later. E equal to I into capital R plus I into small r, or I equal to E divided by capital R plus small r. Terminal potential difference. Consider the adjoining closed circuit where PD, here PD means potential drop, PD between the electrodes is equal to PD between A and B plus PD between B and C, that is across the external resistance, plus PD between C and D. Now PD between A and B and between C and D are 0, since the resistances of the connecting wires are usually taken as 0. Therefore, PD between the electrodes is equal to PD between B and C, equal to PD across the external resistance, equal to I into capital R. This potential drop or difference is called the terminal potential difference of the cell in closed circuit condition. Thus, the potential drop between the terminals of a cell in open circuit, which is EMF, falls to a new value, which is terminal potential difference in closed circuit. Let us begin a new topic, combination of resistors. The topic, combination of resistors, has been deleted by the CBSE for the current academic session, that is 2020-21, on account of the disruption in the teaching learning schedule caused by the prevailing pandemic situation. Please keep it in mind while going through this part of the lecture. A number of resistors may be connected in a circuit as a combination. In the adjoining figure, a group of 3 resistors has been connected across A and B in a circuit. We are interested in finding a single resistor equivalent to the given combination. Suppose the combination in the figure and a single resistor R are equivalent. Then, if the combination and a single resistor were put in a box with just the terminals A and B protruding out, it would be impossible to identify the two by any electrical measurement external to the box. There are 2 basic combinations of resistors, namely the series combination and a parallel combination. Any combination of resistors, however complex it may be, could ultimately be broken down into a number of simple series and parallel combinations. Let us begin with the series combination of resistors. The figure shows 3 resistors R1, R2, and R3 connected in series across a source voltage V. Resistors are said to be connected in series if they occur one after another along a single path. It goes without saying that the same current flows across each resistor. It is I in this example. Let the equivalent resistance of the combination be R. The same current I flows through it when connected across the same source voltage V. In series, the total potential drop V across the resistors is the sum of potential drops V1, V2, and V3 across the individual resistors. That is, V equal to V1 plus V2 plus V3. This is equation 1. Applying the relation V equal to IR, that is I into R, to each resistor in a combination, we get V1 equal to IR1, V2 equal to IR2, and V3 equal to IR3. This is equation 2. And for the equivalent resistor, P equal to IR. This is equation 3. Combining equations 1, 2, and 3, IR is equal to IR1 plus IR2 plus IR3 equal to I, bracket starts, R1 plus R2 plus R3 bracket closes. This is equation 4. Eliminating I from equation 4, we get R equal to R1 plus R2 plus R3. This is equation 5. This is the final result and is also true for n number of resistors connected in series. Now, let us come to parallel combination of resistors. The figure shows three resistors R1, R2 and R3 connected in parallel across a potential difference V. Resistors are said to be connected in parallel if the potential difference across each of them is the same and is equal to the potential difference across the combination. Let the equivalent resistance of the combination be R. Let the currents through the resistors in the combination be I1, I2 and I3 respectively. Applying the relation I equal to V by R to each of them, we get I1 equal to V by R1, I2 equal to V by R2 and I3 equal to V by R3. This is equation 1. If the circuit current is I, then we must have I equal to I1 plus I2 plus I3. This is equation 2. Or substituting from equation 1, I equal to V by R1 plus V by R2 plus V by R3. Or I equal to V bracket starts 1 by R1 plus 1 by R2 plus 1 by R3 bracket closes. This is equation 3. If the equivalent resistor is connected across the same potential difference V, the current through it has to be I. We have therefore I equal to V by R. This is equation 4. Equating equations 3 and 4, we get V by R equal to V bracket starts 1 by R1 plus 1 by R2 plus 1 by R3 bracket closes. This is equation 5. Eliminating V from both sides, we get the equivalent resistance through the equation 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is equation 6. This is the final result and is true for n number of resistors connected in parallel. Let us now discuss the topic electrical energy and power. Consider a current I flowing across a conductor. The potentials of the two terminals A and B of the conductor are respectively V subscript A and V subscript B, where V subscript A is greater than V subscript B, obviously as the current flows from A to B. From now onwards, we'll omit the word subscript from our narration. As usual, we assume that there is no potential drop in a connecting wire. Here, we intend to describe the situation in terms of the flow of the positive charge carriers, although the actual charge carriers in a conductor are the negative electrons. Regarding the asterisks, in most situations, including the one under discussion, the assumed motion of the positive charge carriers in one direction has the same implication as the actual motion of the negative charge carriers in the opposite direction. Let an amount of charge delta Q flow down from A to B in time delta T. The potential energy of these charges at A is UA equal to delta Q into VA. And that at B is UB equal to delta Q into VB. Now, UA greater than UB as VA is greater than VB. So, the potential energy of the charges decreases when they reach B from A in the conductor by an amount delta U equal to delta Q into VA minus delta Q into VB equal to delta Q bracket starts VA minus VB bracket closes. In absence of collisions, the lost potential energy would have been converted to the kinetic energy of the charge carriers. But in this case, Whatever kinetic energy is gained by the carriers is given up in collisions, which they suffer with the iron cores in the lattice so frequently. The lattice begins to vibrate more briskly. This raises the temperature of the sample. Finally, the energy is dissipated in the form of heat to the environment. The energy dissipated in a conductor in form of heat energy as a result of current flowing in it is given as delta H equal to delta Q into bracket starts VA minus VB bracket closes equal to delta Q into V, where V is equal to VA minus VB. The current I is related to delta Q through the relation I equal to delta Q by delta T. Using this relation, we have delta H equal to I delta T into V. Therefore, the rate of energy dissipation, that is, the power is P equal to delta H by delta T equal to I into V. The SI unit of power is volt ampere, in short VA, or watt. The alternate expressions for power are P equal to I into IR equal to I square R, or P equal to V by R into V equal to V square by R. The former expression is appropriate for a series connection of devices, while the later one is for parallel connection. It may be stated that the household connections are always in parallel. This brings us to the end of the lesson 3 of the chapter 3. We will discuss combination of electrical cells and Kirchhoff's rules in the next lesson. Till then, goodbye and thank you.